time, so let's start this session. And I'm the chair of this section. Let me use Chinese probably easier. 是来自阳明交大的李俊。那跟各位介绍其他4位评审。隔壁的这位评审是温文玉教授，来自中原大学。接下来是冯明光老师。然后是谢立教授，来自中正大学。还有李英九教授，来自同济大学。那这一场有3个队，第一个担任 reporter 的是Choco T，Choco T 来自台南一中。然后第一场担任applicant 的是Miracle 来自建国中学。担任 reviewer 的是阿元 AY3 来自武林高中。So let's start the first term. I don't think I need to read this, right? It's already the second day, so probably you all know the rules. So it's 1 minute for opponent challenge reporter for the problem.
We would like to challenge the reporter for problem 11, pumping straw.
We would like to reject.
We would like to challenge the reporter for problem 6, the non-contact resistance.
We would like to reject.
would like to challenge the reporter for problem 4, the shooting rubber band.
We would like to accept.
Can you please try to coordinate? time's up. So now it's reporter to present for 12 minutes.
Okay, so I'm a reporter from S601 and my name is Chen Shi. Today I'm going to report problem number 4, shifting rubber band. So first, here's the problem statement. A rubber band may fly a longer distance if it is non-uniformly stretching when strapped. Given its speed, optimize the distance that the rubber band with spin can reach. So here's our observation video. Okay, so in observation video, we can see that when launching rubber band, we utilize a high-speed camera to capture this event, and this is the unstretched one. So in our observe, so we can know that the rubber band exhibits a rotation upon the launch, and when it launch like in unstretched, and it was just like this shape is kind of like weird, not round, not the round shape. Okay, so here's our theory part. So in our theory, we want to discuss this phenomenon through energy. So first, we have potential energy for my rubber band, and it can transfer to kinetic energy, rotation energy, vibration energy, and loss energy. So according to the laws of energy conservation, we can calculate it. So first, we want to calculate the at the very beginning of this phenomenon, we have the potential energy of my rubber band, and so we can write down our formula just like this. So our potential is, notice this K is the elastic constant. And since we measure the elastic constant of whole rubber band, but in this case, we divide it by like L and LR, L left and L right. So we have to use this L0 over L left or L0 over LR to get the correct elastic constant. So we want to calculate our kinetic energy, we can use this, the upper one, and we can calculate it to here. And now here's the rotational energy. So the rotational energy is defined like this. ER equals 1 over 2I omega squared. And here I present it as a rotation inertia of the rubber band. And in the experiment, we observe that angular velocity of the rubber band is perpendicular to the plane formed by this. So we can just calculate the rotation inertia. Okay. So we define a ratio of potential energy transferred to kinetic energy and the rotation energy. So we call it eta K and eta R. So it's the potential energy, the kinetic energy over the very beginning energy that the rubber band stored it. And we can just show like this and like this. So our rubber band range can express like this after we calculate it. So first, we do some experiment to want to fit our theory. So first, we're stretching our rubber band. Okay. So due to rubber band are an elastic material, so we want to make sure that Hooke's law can apply on our rubber band. Okay. So here's our schematic diagram of our device. So we have a rubber band, and we have some heavy things under it, and we want to measure the relevance between the weight or the force and the and the shape and the delta x of our rubber band. So here's our result that we have a force. So this is force, and this is our delta L in centimeters. So we can observe that during like 50 gram to 300 gram of our force, it's like we can consider it as linear, and the slope is our kinetic. It is our elastic coefficient. So in this range, we think it can apply Ohm's law. And the second experiment, we want to measure the kinetic energy of our rubber band. So we measure our kinetic energy. We observe how long it shoots. So we have our rubber band gun and our rubber band, and we shoot it horizontally. So first, in our very beginning of our experiment, we use chopstick, but it's hard for us to set the uniform stretch. So we designed our rubber band gun through here, and we have sandpaper at the front of it. So we can measure that after we stretch it, and it won't just unstretch before we just shoot the rubber band. And here's our schematic device of our schematic diagram of our device. So note that we calculate our distance from the downside of the very beginning of our rubber band gun, and to the place that rubber band will land. And notice that I have a rubber band, and we measured this place is the top of the rubber band, but not center or the back. And here's our experimental result. And we draw it as a graph. So we can see that. So the first is the uniformly stretched, and when we have non-uniformly stretched, it just go increase. But in some part, it will just got the peak, and it start to decrease. So, no. So this is the range, and we can calculate our kinetic energy. So we want to calculate the eta k, the ratio that our original energy transferred to the kinetic energy. So we can draw a graph and see. Notice that after this it start to decrease. And our third experiment is we want to measure the rotation energy of our rubber bands. So we launch a rubber band and through high-speed camera to capture it, and we calculate the energy. So here is our result of our experiment. And here is we draw our result to the graph. And when it's uniformly stretched, it won't have rotation energy. And when we just ununiformly stretch it, the rotation energy just decrease. So we can calculate out our eta r, the ratio that transferred to the rotation energy. So when we just stretch it, and it will just decrease. Okay, so now here's our conclusion. First, when the rubber band is stretched more non-uniformly, eta r increases. So eta k decreases due to the conservation of energy. And also, because the rubber band is stretched more non-uniformly, the elastic potential energy increases. So the optimal energy transfer will happen when eta k times elastic potential energy reaches the maximum. Thanks for your listening.
So now it's time for question from opponent to the reporters. Story.
I'm going to firstly ask you, can you please switch to page 22 of your slide? Oh, sorry, sorry, 21. Okay, so you have this graph, and I'm curious about the horizontal axis. What do you mean by displaying two lengths? Is that what is the meaning of the two lengths?
Okay, so, okay, I forgot to define it, sorry. So I have a rubber band. So when I stretch it, so I have a round rubber band. So I have the outside part. So like when half. Right. So one side is L left and one side is LR.
So you pin down the 2 points and measure the original length of the.
Yes.
Okay. Thank you. And then which points do you define the initial velocity? Do you, when you can you switch back to the experimental setup page?
Experimental.
You use a rubber band gun to
Right. Yes.
which point do you define the initial?
Okay. So at the very front side.
Which?
So when the rubber band just release from the gun.
The back reaches the back of the rubber band reaches the front of the gun.
No, the front of the rubber band just get off.
And you define the point.
Yes.
Which point? Which point on the rubber band?
Time is up. Sorry.
Thank you.
So duration of the opponent is 3 minutes.
You didn't ask.
So now it's time for all of them to take the floor. So
Good afternoon. I am the opponent from Team Miracle, and I'm the jury. We're going to oppose the shooting rubber band. Sorry for that. Okay. And so for a problem recap, the problem states that a rubber band may fly a longer distance if it is non-uniform stretch and giving it spin. So we think that the key questions is firstly to define non-uniform stretch and spin. Nextly, we want to study that the factors affecting the maximum distance is important. So we think that is the highlight of the question. Okay, so for general pros and cons of the reporter, we think that you have a really well organized report, and you really have a quantified theory to explain your experimental results, and you have different measurements, and you compare the precision of it. The cons is that we don't see any intuitive explanation for it. You just use a lot of formulas, and the fuzzy terminology means that we don't see your definition of non-uniform stretch, and we don't see how you define spin. And we think that you miss an important parameter of initial length, because initial length definitely will affect the potential energy stored in the rubber band. Okay, nextly, okay, so for report overview, we observed that from your preliminary experiment, you observed that if we give it non-uniform spin, non-uniform stretch, there will be wave propagations on the rubber band, and it will fly farther. So we think that you have a clear observation, and you really get a key feature. As for the second step, you do the modeling. You consider energy transfer of potential energy into translational and rotational kinetic energy. And you assumed that the rubber band is isotropic because you used the Case law for springs. Yes, you cited Case law. We think that this model has predicting power, but we think that you didn't mention the limit of the theory. As for the experiments that dive into the parameters, we think that you did parameters such as the non-uniform stretch, the rotational and translational kinetic energy, and you calculated the energy fraction that gets transferred into it. You analyzed it with Excel and bar charts, but we don't see any explanations of your experimental data deviation from the theory. So we think that we think you should have done VT graphs, not just measuring the final distance, because by analyzing the VT charts of the rubber band, we can get a more full picture on the phenomenon. Okay, nextly. So for discussing points later, we want to discuss with you the model. For modeling part, we think the error has some importance on affecting the the distance of rubber bands, because if you have initial velocity, but if you have the same initial velocity but you have different spin, then the Magnus force must affect the distance. Okay, nextly we want to ask you about how do you calculate the moment of inertia if the rubber band actually deforms when you shoot it? For experiments, we want to ask you how do you release the band? For experimental setup, we want to ask you if have you controlled your shooting gun parallel to the ground?
Yes.
You do, okay. And how do you remain the non-uniform stretch when using a gun? Because
since we have sandpaper at the very front of it, so when we just got the non-uniform stretch and we place on our gun, then the sandpaper will make it not going to stretch, turn to the uniform stretch. I don't know how to say it. Yeah. So
where's the paper you mentioned?
Sandpaper here and here. So.
Sandpaper. You mean you increase the friction in your points you pin down.
Yes.
Okay. So you maintain the non-uniform stretch. Okay. But we did see where is your definition of non-uniform stretch. You mean we think that you should use a single parameter to include all the non-uniform stretch, not just doing two different. So like you define non-uniform stretch as the difference of the two lengths, or as the ratio of the two lengths, or anything else.
We define it as the ratio.
The ratio, okay. And what does this ratio say about your experimental data? Because can you please switch to the data page? There is an apparent deviation from your theory that when it is non-uniformly stretched to a degree, it suddenly the maximum distance suddenly decreases. How do you explain this phenomenon according to your theory?
So since in our theory, the non-uniform stretch can increase the whole potential energy of before I just shoot the rubber band. So the energy that the rubber band stored is bigger, right? But when it stretched just stretch too much, then the energy will transfer more to the rotation, but not increase the kinetic energy.
But if you said how do you define too much? What is the too much?
Okay, so sorry for I used the wrong word and.
No, I don't.
In our graph, so in some ratio it has the maximum, but over it starts to decrease.
So I mean, if I plotted the maximum distance against the ratio of the two lengths, then if the ratio is too large to an extent, then it will decrease.
Right.
And you explain that by using that the rotational by giving it too much stretch, then it will give too much energy to rotational energy, and then the maximum distance will decrease. But there are obvious energy transfers to rotational energy before this ratio. How do you identify the critical ratio? I mean that by giving it a non-uniform stretch,
yes,
definitely it will have spin. You observe that.
Yes.
And why does if all cases of non-uniform stretch give it spin, then why does the ratio over a critical value and then the maximum distance decreases? I don't get it.
So can I use the blackboard to explain it? Okay, so since I have sandpaper right here, okay, then here's my rubber band.
Yes.
And I gave it non-uniform stretch.
Yes.
But before it has really it has a before it just shoot up, and so so when the sandpaper still touch my rubber band, then in this time duration, the rotation energy will keep increase because I release from here, and the non-uniform stretch just start to like the energy difference just start to release and start to balance. So it starts to rotate, right?
Yeah.
So it starts to rotate. But so when it's overstretched, so it rotates more faster in the same time duration.
Yeah.
So it gives too much rotation energy that makes the kinetic energy just go decrease.
Okay, I see. And now, okay, I see. Thank you. And next, let's go on to the next question. How do you play your camera? Can you show me the experimental setup?
No. I draw it. So this is our rubber band gun.
Yes.
And this is my floor.
Yes.
And I put camera here, just camera.
How can you see the wave propagating on the rubber band?
Probably so when we are observing the kinetic energy. So we place the camera here.
Yes.
And if we want to observe the wave just like our observation video, we put the camera here.
Yes.
To take the videos of this region.
Okay, so when you want to observe the waves, you change the camera position, right?
Right.
Okay, thank you. And I think that when the rubber band is getting shooted out, its direction will definitely change. So how can one camera just capture all the information you needed? How can you trace the rubber band's position?
So you mean if I have my view just from here to here, the rubber band will just like this? Will just turn, or you mean what?
I mean that if you are observing, you mean that you put camera on. If I'm the camera, I'm seeing this.
Yes.
And the rubber band, you said that you put the gun horizontally, parallel to the ground. But the rubber band will deform after the stretch. So how can my camera see the non-uniform stretch? How can I observe the whole process if the rubber band is deformed? It will change position. It will definitely go down. So it will change the.
Sorry.
Oh, sorry.
Can you just draw?
Okay, sorry.
I
Next.
really understand.
I'll go to the next question. Sorry. Nextly, we want to discuss the moment of inertia with you. How do you calculate moment of inertia if the rubber band has deformed? If you have non-uniform rubber band, how do you calculate the moment of inertia?
So since after I shoot it, then the rubber band will just spin in like somehow this place or this place. So I can just calculate the inertia.
Based on what?
Based on its wait, you mean the movement or the spinning?
When the rubber band is flying, it will definitely. You mentioned that there is a wave propagating through the rubber band when it is flying, right?
Right.
But if it has a wave, then the mass isn't distributed evenly on the rubber band. So how do you calculate moment of inertia based on the non-even distribution of mass?
Okay, so it's uneven distribution here at the beginning of this process, but at the middle, at the end, it just go to like we can consider it as a like circle or the oval
or an ellipse or something.
Yeah, so we can just calculate this.
Okay, so you've done integrals or something. Oh no, okay, I see.
So time's up.
Okay, thank you.
So now it's time for opening to summarize the discussion.
Hey.
1 minute.
Okay, so as for the summary, I asked the reporter how to define non-uniform stretch, and they concluded with they defined the non-uniform stretch as the ratio of the two lengths. They divided the rubber band in. Okay, and I asked that why does the maximum distance suddenly decreases after non-uniform stretch, and they concluded that when the non-uniform stretching reaches a certain amount, then the maximum distance will decrease. And then I asked the reporter how did they calculate it? How do they calculate the moment of inertia? And they said it is a minor process when the rubber band is flying out. Thank you.
Reviewer. Opponent.
Okay, so my first question to the reporter, I want to know how did you get your angular velocity?
Okay, so here I have camera, and I have mark on my rubber band. So I take camera, and I take the video, and I can use tracker to analyze it.
But you didn't mention it in your report.
Sorry, that's my fault.
And how do you think about this? You did not mention that you did not. I mean, the opponent did not mention that the reporter hasn't talked about how they observe the angular velocity.
We think that the mark we think that if they put a mark if they put marks on the rubber band, then we can track the angular velocity, but it has some problems about the mark is stretched. So we think that if the mark is stretched, then we cannot analyze the situation pretty clearly.
So you don't agree with that?
We think that you shouldn't put a mark. You shouldn't put a mark directly on the rubber band because it will stretch it with it.
Okay. And then for the reporter, so you use the Hooke's law, right?
Right.
And but you show the PowerPoint. So I remember that there's an intercept, like.
Right. So there's you mean the area that changed when we stretch it?
No.
No.
So from this graph, I remember there's a intercept, like. So yeah, so f is not directly equal to.
Right, but so in this region, we think because the r squared is equal to 0.9795, I think it's enough for us to say it just fit the Hooke's law in this condition.
Oh, because r is close to 1, so.
Yes, right.
For the opponent, do you agree with this?
You mean he's testing the Hooke's constant, spring constant?
Now, do you think that for the reporter they can use the Hooke's law to?
They didn't mention the Hooke's law is limited by within the linear range. So if it is going into plastic region, then it will not work. But we think that
Time is up, sorry. So it's a preparation for the reviewer. 2 minutes. stop. 4 minutes.
We're the reviewer, and the topic is shooting rubber band. So first, this is the summarize of the reporter. First, they have a problem and video. So they demonstrated the problem with a video. And then they did the experiment with different parameters. And they have the theory of energy, including kinetic energy, rotational energy, vibration energy, and energy loss. And at last, they had a conclusion from the video. Okay. For the reporter, they have some strengths, including clear voice and clearly introduced the theory, and also the uncertainty of the data. But for some areas of improvement is that they planted some theory not accurately, and they missed some parameters, for instance, initial length. They did not completely analyze the data, and they have lack of explanation of the spin effect, and they did not mention the angular velocity. For the opponents, the strengths are, first they organized the reporters missing. They did a detailed discussion of their presentation, and they pointed out some lack of the experiment slide. And just as I said, they did not mention initial length or something. And for the areas of improvements, they still missed some of the reporters' problems. So here is the discussion part. So first, the opponent says that the reporter did not clearly define what is non-uniform. And for the reporter's response, they say that the ratio of strength on two different sides is their definition. And then the second, the opponents say that the distance decreased at a higher ratio. And for the reporter, they think that this happened because some energy transferred more to rotation. At this part, we agreed with the reporter because kinetic energy might transfer to rotational energy more. And then here's something about the camera setup. And the opponent thinks that the camera setup cannot capture the motion well. And yeah, because it's a three-dimensional motion, and they think that it's not, so they need to put more cameras. And for this part, we agreed with the opponent. Okay. And also, for the Hooke's law, the reporter, because they think R is close to 1, so they use the Hooke's law. But to this part, the opponent does not agree with this. And another thing is about the angular velocity, which they did not mention how they get it at first. So for the reporter, they said that they put some marks on the rubber band, but for the opponents, they did not agree with this because they think that when the rubber band was full, it will not be accurate. Okay, that's all. Thank you.
Okay, so here's the concluding remarks of reporter. So first, the reporter summary. The elastic potential energy is transferred to kinetic energy, rotation, and wave energy. The elastic force can be calculated using Hooke's law, and non-uniformly stretched will have a higher kinetic energy than one is uniformly stretched that we proved in our experiment. And the optimal distance a rubber band will reach it when the product of eta k and the elastic potential energy reaches the maximum. And here's our discussion summary. So first we discussed about how the rubber band gun works. And we discussed about why there was a peak when we stretching the rubber band. And it stretched too long, and more energy will be transferred to rotation energy rather than kinetic energy. And we discussed how do we calculate the moment of inertia and about how we place our camera. And here's some concerns results. So first is we marked out our initial length in our PowerPoint. And within the stretching distance of our experiment, the rubber band obeys Hooke's law within the range that we tested. And while it may not obey if we stretch even more. And the moment of inertia can be calculated using mr squared because we observed that the rubber band appeared to be a circular shape in the middle of the flight. But so the opponent and reviewers are concerned about at the very beginning. So at the very beginning, it's very hard for us to analyze it. So we choose the middle or the end of our flight to analyze it.
Okay, hands up. So now it's time for Yuri to ask the questions. Is there any questions from you?
So, question first for reporters. You use the Hooke's law.
Yes.
Yeah, to model the rubber band. Do you think it's a good model, or in any case it's not applied to the rubber band?
So if we stretch too much to our rubber band, the cutting area of my rubber band just will decrease. So in our case, we didn't make it. The decrease of the cutting area is not very obvious. So in our first experiment, we proved that we can apply Hooke's law just in the case that we test our experiments. But for the more we stretch, and it might be some conditions that it can't apply the Hooke's law, and now we have to use the Young's module. But we didn't consider it in our experiment. In our theory.
So maybe same question for others.
We think that the Hooke's law is applicable when you're stretching it uniformly, but if we have a non-uniform stretch, it will definitely cause shear forces, which is not describable directly by Hooke's law.
Reviewer?
So for the reviewer, we did not agree with the reporter, so we do not think that Hooke's law can be applied in this situation. Because F is not proportional to X, and there's
Yes.
I just want a simple answer. Just yes or no. Is it possible to separate the energy into translation energy, which is kinetic energy in your term, and rotation energy? So I summarize this. Is it possible to separate energy into translation energy and rotation energy? Is it always possible? Yes or no?
Yes.
Yes. Okay.
No.
Sorry, can I just fix? So I think yes in this case, but no for the whole like loss of this. I don't know how to say that.
Okay, I have a following question for the reporter and also related to that. Someone asked that is this experiment follows the Hooke's law. I remember in your presentation you said that there is some overstretch or something.
Okay.
So why do you still think this follows Hooke's law?
So we said the overstretch is the kinetic energy just start to decrease, right? So we said overstretch means that, but not the overstretch that we can apply to in
So
our
even
experiment.
under this overstretch condition, still is power split.
Yes, in this condition.
So what is your opinion?
I think that he defines the overstretch as experimental observation, which is fine, but we think that he didn't look into the situation to find out if it actually fits the case law. So we think that it is still not resolved.
So the reviewer's opinion?
I think there can be like a more accurate way to, like, instead of doing I say that I don't think it's appropriate to use flip flop in this situation, and I believe there should be some other more accurate way to use flip.
So time's up. So let's give 1 minute for jury to write down the calculate their scores. So first they need a score for reviewers or reporters. I'm sorry. So the score for reporters. So 8, 4, 7, 7, 6. Next, okay. So next would be the score for opponents. So it's 6, 4, 7, 8, 7. Finally is the score for reviewers. So it's 6, 4, 5, 6, 6. Thank you very much. We have 15 minutes break.